evaluate the performance of the sensor in presence of ammonia gas. So here we start with the introduction where this SAR-based gas sensor is a MEMS-based device which is used to operate in the range of megahertz to gigahertz. Mainly, this surface acoustic wave sensor, its totally operation is based on generation of surface acoustic wave sensor. Here shows the basic block diagram of the surface acoustic wave sensor, and the figure B represents the basic block diagram of surface acoustic wave sensor. Here, the surface acoustic wave sensor consists of four important parts. Mainly the piezoelectric substrate, which forms the basement for the sensor, and secondly, the input IDT and the output IDT. This input IDT stands for interdigitated transducers, and this input IDT and output IDTs are wrapped within a sensing layer, which is placed over the piezoelectric substrate. And the operation is as follows. Now, this when we apply the electric signal at the input IDT, this input IDTs are provided with the alternating potentials like alternating positive and negative potentials. When an electric signal is applied to the input IDT, the pressure which is developed on the input IDT will convert that electric signal into the acoustic signal. So the pressure is developed by the piezoelectric substrate, which provides the basement for the sensor. And this acoustic signal, which is generated, will propagate over the surface of the sensing layer, and it transfers to the output IDT. At output IDT, the potentials replace the same of alternating potential, and the output IDT, once again it gets converted, the acoustic signal gets converted into the electric signal. So during the transmission of this signal, so gets this is impressed by the electric properties of IDT and electric and mechanical properties of the sensing layer, and also the electric and mechanical properties of the piezoelectric crystal. So this surface acoustic wave sensor, which is developed here, it is imposed by three characteristics like frequency, magnitude, and the phase. So these three parameters which are developed or based upon the properties of IDT, piezoelectric crystal, and the sensing layer. Now, when we impose the external parameters like gas over the sensing layer, it causes a change in the three parameters of the surface acoustic wave. So like it may get a change in the velocity, it may get a change in the amplitude of a signal, or in change in the frequency, or in the phase. So now here, this is the proposed device for detecting of ammonia gas. So here are the IDTs which we have designed, and these IDTs are the input IDTs, these are the output IDTs, and this is the piezoelectric crystal, and this is the sensing layer. So this surface acoustic wave sensor has wide varieties of applications. It can be used as a gas sensor, it can be used as a chemical sensor, it can be used as a mechanical sensor like pressure sensor, it can be used as a force sensor too. So when we are using the surface acoustic wave sensor for the different applications, the physical parameters which we are identifying will cause a change in the properties of the surface acoustic wave. So that properties which undergo a change of surface acoustic wave, or it can be the mass of the sensing layer, or it can be the density of the sensing layer, it can be the velocity of the acoustic wave, or it can be the elastic modulus of the sensor, or it can be the electric properties like conductivity of the sensor, or it can be the temperature of the sensing layer. Now, in our study, we have considered the change in the acoustic velocity, which is identifying the presence of the gas over here. And now, for this designing of the sensor, we have gone through some analytical modeling, and that analytical modeling deals with the following expressions. So here we have designed, when we come with the surface acoustic wave sensor, we are mainly focused on the operating frequency. This operating frequency is denoted with SNR, which is a function of acoustic velocity and acoustic wavelength. Here, this acoustic wavelength deals with the IDT width and the IDT spacing. So now, with the increase in acoustic velocity comes with this V is acoustic velocity and lambda is the acoustic wavelength. Acoustic velocity comes with the piezoelectric material, and lambda here it is expressed as twice of this electrode spacing. Now, here the amplitude of this surface acoustic wave sensor is greatly influenced by the electromechanical coupling coefficient. This electromechanical coupling coefficient deals with the how efficiently there is a bonding between the sensing layer, IDTs, and the piezoelectric crystal. So higher this electromechanical coupling coefficient, higher will be the performance of the sensor, better will be the performance of the sensor. So in order to have the better electromechanical coupling coefficient, we have chosen the lithium niobate for this purpose. And the surface, and over the surface, we are dealing with the deflection of the sensor. This deflection of the sensor is expressed with a D here, and this D is a function of matrix, strain matrix of a particular piezoelectric material, coupling matrix of the piezoelectric material, and also the electric potential which is existing over the sensing layer. Now, when we come with the amplitude or the frequency generated for this design sensor, we need to concentrate on the coupling coefficient and the piezoelectric coefficient and the permeability constants. And here are the coupling coefficients and the piezoelectric constants and the permeability constants which we have taken to have a better response from the sensor. And now the values corresponding to this here, the elastic coincidence, with the varying of the elastic coincidence, there will be the much variation over the response of the sensor. Now we have taken this in the XY, we have taken the piezoelectric substrate to work in the XY plane, and with this XY plane, we have defined this elastic coincidence and the piezoelectric coincidence. And the density is considered to be 47,000 kg per meter square for this particular piezoelectric material. And with this design constants, and we have designed this in the console by using these dimensions. The piezoelectric substrate is taken with a 500 micrometers of width, length, and the height is considered to be 1,000 micrometers, and the IDT is taken with a width of 5 micrometers and a height of 140 nanometers, and the sensing layer is taken with a length of 5,000 micrometer with a height of 150 micrometer. The electrode spacing is provided to be 5 micrometers, and the space between the two electrodes, that is the input IDT and the output IDT, is to be 4,000 micrometers here, which we call it as a pitch. So now with this design constants, we have designed the proposed sensor in the console by using the solid state studies and the piezoelectric studies. By using this solid state studies, we have defined the dimensions for the sensors and even given the potentials for the IDTs, and we have defined this periodic conditions and the dimensions and the electric conversation between the piezoelectric crystal and the sensing layer. Now the design sensor, this is a design sensor in the console, and this is the machine done in the console. This sensor is studying in presence of ammonia gas and also without the ammonia gas. Now, without the presence of ammonia gas, the design sensor will produce some deflection with respect to its operating frequency. Now, when we impose the ammonia gas, due to the imposition of ammonia gas, it causes a change in the electric conductivity of the sensing layer, which causes a change in the characteristics of the sensing layer. So now this is the proposed design where we will be imposing the ammonia gas and also will be studying without the presence of ammonia gas. So now, without the imposition of the ammonia gas, so here is the response of the sensor with respect to the displacement. So here the sensor is operating at a frequency of 3 megahertz with a maximum displacement of 5.27 nanometers. And now here we can see the displacement in presence of gas and without the gas. So now here it is very clear that without the gas the displacement is high, and with the imposition of gas over the sensing layer, so the displacement has decreased. So this decrement of the displacement is due to the change in the mass loading which is taking place over the sensing layer. So now with the change in the mass loading, it causes a change in the velocity of the acoustic wave. So here, even though there is a change in the mass loading, here we are considering the mass of the sensing layer to be constant, and we are concentrating with the velocity of the sensing layer. Now, with the imposition of this ammonia gas, it causes a change in the deflection and also the change in a shift with the frequency. Now, with the imposition of this gas, there will be a change in the displacement, like it is around 1.92 micrometers, and it is at 10 ppm of gas, where there is a change in the displacement with respect to the concentration of gas too. Now, when we impose the gas, so this is the displacement at 10 ppm of gas concentration, and this is the displacement at 100 ppm of gas concentration. With the variation of the gas concentration, there is a continuous variation of displacement over a frequency range. So when I have varied the frequency in the range of 1 megahertz to 10 megahertz, this is the range. This is a variation of the displacement at various frequencies. Now, when I consolidate with the displacement with respect to the hydrogen gas, the displacement with nitrogen gas with respect to gas concentration is like this. So the displacement is increasing linearly with respect to the gas concentration. Now, when I take with the same representation of this displacement with respect to the nitrogen gas, I have represented in the form of a stepwise. The stepwise linearity, here in the stepwise linearity, we are considering the mass density to be constant, where there be a change in the velocity of the acoustic wave. So the design sensor has identified the nitrogen gas, where in the presence of the nitrogen, without the presence of the nitrogen gas, the displacement is high. In the presence of the nitrogen gas, the displacement has decreased, but with the increase the nitrogen gas concentration, the displacement has increased. So that is regarding the proposal sensor, what we have done. And here are the some references which we have used for the simulation and for the study. And I acknowledge this Sri Vidyaniketan Engineering College, which has provided me the console multiphysics software. And thank you for giving me this opportunity. Thank you all.